Today we start a new chapter called Rational Functions. And Rational Functions is a much more difficult chapter than the previous four. So if you've been cruising along through the different days' homework and doing some of it, but not necessarily all of it, and that's still gone well for you, you've still understood things very well, that actually is possible. Those chapters aren't that difficult. But Chapter 5 is not going to put up with that. So if you've been not keeping up with the homework and so on, today's the day to get going again, because Chapter 5 has a lot to understand and a lot to know, and you've got to get through all this homework to really understand what's happening. The first day of this chapter starts with graphs of reciprocal functions. And what we mean by a reciprocal function is, last chapter we were talking about polynomials, but now what we're going to have is 1 over some polynomial. So all those polynomials, all those skills we got around polynomials last chapter, we're still going to use them, but we'll be analyzing the denominator. And that has some very specific implications that we need to talk about. And once we have those implications down, we can use all the weapons we used last chapter to attack the graphs here. Just a couple of notes before we start, though. I want to talk about a couple of division statements before we even get going. I've got my calculator out here beside me to type these in, and I encourage you to type these in so these are clear. It may be that you see this is no big deal, but this is really the heart of this lesson of understanding what these numbers mean. If you go 1 divided by something large, and I'm going to use 1,000 as my large number because 1,000 is large enough that I can make the point I want to make here. And when I type in 1 divided by 1,000, I get 0.001 when I put it in my calculator. And the implication there is that when I go 1 divided by something big, I get something close to 0. And I'm going to use that thinking as I go along in this section. So 1 divided by something big is something very, very small. I say close to 0 because that's going to really help us to think what we mean by small. Next, 1 divided by something small, so I'm going to divide by that same 0.001 that I divided by just a second ago. And if I go 1 divided by 0.001, and some people really need to type this in to really confirm that this is true, when you go 1 divided by 0.001, you get 1,000. That is shocking when you first see it sometimes, because when you first learned division way back in grade 3 or 4 or whatever it is, what you found out was that when you divide by something, it gets smaller. That's always the way it worked. When we divided by something, we got smaller. But we didn't divide by really small numbers like we were dividing by here. And so that means that we have to have a new understanding of division. That it depends on what you're dividing by, whether you get a bigger or a smaller number. One way to think about it is if you're taking $1 and dividing it into pennies, something really small, what do you get? You get 100 pennies. You get something very big. So if you're dividing something into very small pieces, you get a lot of pieces. The implication here is that when I go 1 divided by something close to 0, I get something big. And the last one, which is really sort of obvious, is 1 divided by 1 is 1. When you divide by 1, you get 1. You get the same answer back. Now I'm going to do this all the same thinking and maybe bore you a little bit, but do it with negatives. And to show that negatives, there's only one real change that comes on here. So if I go 1 divided by negative 1,000, I get negative 0.01. And all that's happened is when I go 1 divided by something that's negative and big, I get negative close to 0. So all that's happened there is I've changed when I'm dividing by something negative, I get a negative answer. Okay, how about 1 divided by negative 0.001? That's the one that some people have to type in their calculator to reassure themselves this is true. I get 1 over negative 1,000. So if I go 1 over something negative close to 0, I get a negative big answer. I hope you know what I mean by negative big. Negative far from 0. And then 1 divided by negative 1 comes out to negative 1. So the only thing that's happened in the right-hand column here is that when I went to negative, everything I did switched to negative. When I was dividing by negative numbers, I got negative numbers. That's not all that surprising, I don't think. Okay, to tie all this stuff together. Consider the graph of y equals x. Hopefully y equals x is something you're familiar with. all the y values are the same as the x values, so I get these points 1, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and then same into the negatives. Now let's think about the graph of the reciprocal function y equals 1 over x. Actually, in grade 11, you study y equals 1 over x, so you may already know what the graph's going to look like. But I'm going to make up the graph y equals 1 over x using the graph x in a very specific manner that allows me to handle other situations. So if you've got it memorized, that's great, but the memorization isn't going to help you move to other reciprocal functions. So 1 over 2x squared plus 5x plus 9 or something like that. So I'm going to analyze this in a slightly different way. What I'm going to look at is if I'm looking over at this part of the graph, over near 10 here, and I look at what the graph is, and its value is about 10 up there. I'm trying to graph 1 over x, so that's 1 over 10. And 1 over something pretty big here, 1 over 10, gives me something pretty small, specifically 1/10. So my graph is way down here. I'm going to jump over to about x equals 5 here, and when x equals 5, this graph has y value 5. But I want to do 1 over that. And so 1 over 5 is like 1/5. That's still pretty small, but it's not as small as it was. Still pretty close to 0 there. Where's the breaking point in all this? Where does that end up? Where do these things break even? Well, at the value 1. At y value 1, 1 divided by 1 is 1, and so this graph will be 1. So all through here, I get these values here. Because this y equals x is getting bigger and bigger and bigger, the 1 over x will be getting smaller and smaller and smaller. The bigger it gets, the bigger y equals x gets, the smaller y equals 1 over x gets. Now here's a really interesting part of the graph. If I look right in here, right in this section here, from 0 to 1, if I'm dividing by numbers that are getting closer and closer and closer to 0, I'm going 1 divided by 0.5, then 1 divided by 0.1, then 1 divided by 0.01. As I divide by these bigger and bigger numbers, if I go 1 divided by those smaller and smaller numbers, I get bigger and bigger numbers as a result. Think about 0.001, which we just did on the previous slide. 0.001 is super close to 0, and its value would be 1,000. Right off the page here. So as we get closer and closer to that 0 value, the answers get bigger and bigger. Now what happens when you go 1 divided by 0? Well, you can't do 1 divided by 0. So I'll just switch over to another color here. So what we get is this vertical asymptote. Where the original function is 0, we're going to get a vertical asymptote, which means the function can't exist here. When the y value is 0 on the original graph, the reciprocal graph will not exist. Let's go to the left-hand side and do all the thinking again, but with negatives. At the value negative 10, the x value is negative 10. The function value is also negative 10. And when I go 1 divided by negative 10, I get something very small, but negative 0.01. As I get farther away from that, the numbers aren't as big as they were. So like, for instance, 5. And 1 divided by negative 5 is like negative 0.2. Still pretty small. Where does this thing break even? Well, at negative 1. When the y value is negative 1, I go 1 divided by negative 1, I get negative 1 again, and what I get is this section of the graph here like that. Put a little arrow on there because that keeps going closer and closer to the x-axis. And then this section in between 0 and negative 1. Sort of difficult when you first think about it. The idea is that as you get closer and closer to 0, as you're dividing by numbers that are smaller and smaller and smaller, what you get is bigger and bigger answers. Think about the 1 divided by negative 0.01 on the previous page. When we divided by negative 0.001, we got like 1,000. So as I get really close to an x value of 0, what I get is a very large y value, but negative this time. Now, I hope you know that graph already. You've seen that graph in grade 11, but that's a different development. And that thinking I just did there will allow us to address other reciprocal functions. So if you're having trouble anywhere along in this lesson, come back and watch the video for that slide again to make it clear the basic plan here, because the basic plan now won't change through the rest of the lesson. Let's talk about positive and negative intervals. Where the function y equals x is positive, the function 1 over x will be positive. If you've got 1 and you're dividing it by something positive, you'll get a positive number. And where the function y equals x is negative, the function y equals 1 over x will be negative. When you're dividing by something negative, and you go 1 divided by something negative, you'll get something negative, and that reflects in the graph. Domain issues. Where the function x is 0, the function 1 over x will be undefined. You can't go 1 divided by 0. Increase and decrease. As the function y equals x approaches infinity, the function y over x will approach 0. And as the function y equals x approaches 0, the function 1 over x will approach infinity or negative infinity. So as we approached the 0 there, things went off to infinity. And the intersection point is when we have y values of 1 and negative 1, because when you go 1 divided by 1, you get 1. And when you get 1 divided by negative 1, you also get negative 1. You get the same thing back out at those particular y values. So here's the graph, as I showed you on the previous page there. There's the graph y equals 1 over x. Notice the vertical asymptote at x equals 0. So that was the asymptote going straight down the center here. But there's also a horizontal asymptote at y equals 0. So there's this horizontal asymptote that this graph approaches out there. We're going to talk a lot about vertical and horizontal asymptotes this chapter. So more of the same. The ideas in the previous example can be used to graph the reciprocal of any function that we know how to graph. Consider the following examples. Okay, here's y equals 2x plus 3. Hopefully you know how to graph y equals 2x plus 3. It has a y-intercept of 3. And it goes up by 2's. More importantly, it goes through 0 at negative 1.5 here. If you sub in y equals 0 there, you'll get 0 equals 2x plus 3. And if I solve for x, I get x equals negative 3 halves. So I have the x-intercept there that I can use for my graphing here. Now I did that all in green, so I'm just going to switch colors here so that I have a different color to use for my graph. The important thing here is there's a vertical asymptote right here where y equals 2x plus 3 is 0. If I go 1 over 0, I get a vertical asymptote. It can't exist there. You can't go 1 divided by 0. So where the y values of my original function are 0, when I go to do the reciprocal function, I get a vertical asymptote there. The rest of it is just the thinking I did previous. That is, as the function gets very big, for very big y values, well, I'll get very close to 0 y values in my reciprocal. As the function gets very close to 0, I get very large y values, positive. And then right there, there's the intersection point where the y value of the original function is 1. When I go 1 over 1, I get 1. Similar thinking on the negative side. Big negative values here give very small negative values for the reciprocal function. Where it's negative 1, I get negative 1. And when I'm going to very small y values, I get very big y values on the reciprocal. Y equals x squared. If I want to do the reciprocal of y equals x squared, I look and go, okay, where y equals x squared is 0 right there, I can't go 1 over 0. So I get my vertical asymptote there. Where are the intersection points? Where the y values are 1. And then where y equals x squared goes big, 1 over x squared goes very small. Where y equals x squared goes small, 1 over x squared goes very big. Now, sort of two spots you can be at that point. You either totally get that and you're like, oh yeah, I'm okay. 1s become 1s. Close to 0 becomes big. Close to, when you get really big, that becomes close to 0. Or it's very confusing to you, in which case you should start the whole video over and watch up to that point again so that you go, oh, I get it now. Because that's really the whole heart of the lesson right there. One more, this one slightly more complicated, y equals x squared minus 3. To find those y-intercepts, if you set that equal to 0, set the y value equal to 0, what you get is x squared equals 3, and so I need plus or minus the square root of 3 as my x-intercepts, and it's plus or minus about 1.7 if you put that in your calculator. So that's where these two x-intercepts come from for y equals x squared minus 3. This is the graph of y equals x squared moved down 3, so it's got a vertex down there at 3. Now there's lots to talk about here. Some of it is simple. on my graph of my new function, which I'll do in green, maybe blue will show up nicely on here. Here's the whole procedure, top to bottom again. If it's sort of clear in your mind, but not really perfectly clear at this point, where these y values of my original function are 1, my new function is going to go through those points because 1 divided by 1 is 1. Where the old function was 0, I'm now going to have a vertical asymptote because you cannot go 1 divided by 0. So there's a vertical asymptote right there and a vertical asymptote right there. Over here, where the graph is positive and big, I'll now be positive and getting closer and closer to 0. Where this graph goes to 0, y equals x squared minus 3, the reciprocal will go to infinity. It'll get bigger and bigger and bigger. And that's true on both sides here. So those two sides use a lot of the same thinking that I was using in the previous examples, that 1 becomes 1, big becomes small, and small becomes big when you do reciprocals. This section is very, very strange and very difficult to draw. When you do 1 divided by -1, you get -1, so there's going to be a point right there, and then there's going to be a point right there, the 2 times where it was equal to -1. And then this point here, y equals -3, becomes 1 over -3. That's very strange because you know the y value this time. You know the y value is -3, so you've got to go through a y value of -1/3. And I'll have the graph pop up on the computer screen here now. I sort of got lucky where I put that point that it was right on. So lots of thinking to go through, one thing at a time. Where it's 1 or -1, those points stay the same. Where the graph gets really big, the reciprocal will get really small. Where the graph gets really small, the reciprocal graph will get really big. And one last little piece of the puzzle, if you know a specific y value, which we did a -3 here, then the reciprocal graph will have a y value, a point there with y value 1 over that value. So -3 became 1 over -3. Difficult example. So bad news here, these are difficult examples. The good news is they're pretty repetitive. There's no extra tricks than what you've seen so far. Give it a try. All right, I'm going to sketch the graph of the following functions on a separate page. So here's the plan here, is that instead of graphing y f at x equals 1 over 3 minus x, first I'm going to graph y equals 3 minus x. If I graph 3 minus x, then I can do this reciprocal thinking afterwards. So I'm going to go to this next page here. I'm going to graph y equals 3 minus x. Let me just color code this. Here's my graph y equals 3 minus x, which I'm going to write as -x plus 3. That's the way most people will be used to seeing it for y equals mx plus b. So what I'll get is y-intercept 3 and slope -1. Now I don't have a really great way on my computer here to draw this straight line, so I'll just do the best I can here. Something like that. How'd I do? Sort of fell off the map there. It'll be enough for what I have to do here. So now what they want is the graph of, and we'll need another color here to color code this. I'll do it in green. I want to graph y equals 1 over 3 minus x. I'm going to do that in green. Here's the procedure. Where the graph is 0, and I missed slightly there, it's 0 right there at the x value 3. So where the original graph was 0 at x equals 3, now I'm going to have a vertical asymptote because my 1 over graph will be 1 over 0, which is undefined. Next, invariant points, where this y value is 1, right there, and -1, it was supposed to be right there. my new graph will go through those points. As this graph gets very small, this graph gets very big. As the red graph gets very big, the green graph will get very small. But keep its sign, it's still positive. As the red graph gets very big over here, the green graph gets very small. And as the red graph gets very small right in here, the green graph gets very big right there. That's the procedure. Graph the original function, look at the 0, look at the 1s, and then the big small stuff. That's not all there is to the story, but that's pretty close to the whole story. One more example. What do they want here? Ooh, 1 over negative 2x squared minus 12x minus 14. This is going to need a little bit of work to get going on it first. Because what I'm going to do is try and graph y equals negative 2x squared minus 12x minus 14, which is not a simple thing to graph in the form it's in right now. It's in what's called general form, and general form is not simple to graph. There are other advantages to general form. For instance, if you had to do the quadratic formula, there's some advantages here, but in this particular case, this is not a great form for graphing. The form I want for graphing is vertex form, and to get from this form into vertex form, I've got to complete the square. So the steps to complete the square. Factor off the leading coefficient off the first two terms. Then add and subtract this magic number, which is half of the 6 squared. So half of 6 is 3, squared is 9, so I get plus 9 minus 9. And the reason you do that is because that makes this into a perfect square. That factored is x plus 3 squared. Multiply the negative 2 times the negative 9, I get positive 18. And now, I keep writing that x there, negative 2, x plus 3 squared plus 4. Now I'm ready to graph that thing. Y equals negative 2, x plus 3 squared plus 4. On to the next page. That thing had vertex at oh, I don't have a graph there. That's no good. Oh, I thought I put another graph in there. Just give me 1 second to find another grid to work on here. Okay, negative 3, positive 4. There was the vertex opening down, and it's going negative 2 over 1 down 2 over 1 down 6. So down to negative 8 there. Down to negative 8 there. there, finally, is the graph of y equals negative 2x squared minus 12x minus 14. Yes. That's not what I'm wanting to graph. I want to graph, let me get a different color here, go in here. I want 1 over negative 2x squared minus 12x minus 14. Here comes all the thinking here. Where this graph goes through 1 and negative 1, those points will stay at the same value. Where this graph is 0, there's now a vertical asymptote going right down through there. And here, a vertical asymptote going right down through there. And I've got a point here, negative 4. That's now going to go through negative 1 over 4. And then where this purple graph gets small, the green graph gets big. Where the purple graph gets small, the green graph gets big. Where the purple graph gets small, the green graph gets big, but negative now. And where the purple graph gets big, the green graph gets small. Very hard to see all the details here. Big purple graph, small green graph, small purple graph, big green graph. Okay, so that's what the graph of y equals 1 over negative 2x squared minus 12x minus 14 looks like. All the steps are there now. One more time, the steps. Graph the original function. Second, put on the vertical asymptotes. Where the original graph goes through 0, we'll now have vertical asymptotes. Put on your invariant points. Where the y values are 1 and negative 1, those points will stay the same. And then where it's big, it becomes small. Where it's small, it becomes big. The only extra little thing is, if you've got a specific point, then you can make another specific point out of that. Okay, give that stuff a run. I will not claim it's easy. You reach out as soon as you have trouble with any of it, and see if you can map your way through this, because it's just going to ramp up from here. So do all you can on that.